Okay, the talk about convex category and contextuality, how we can use convex category as approach of contextuality. So let me start. First of all, let's start from the definition of real convex sets. Now, real convex sets doesn't have to be inside the vector space, it's just a set with this operation. Like, what is this operation? Tell us that I can do a convex combination, okay? Like this is represent a convex combination, which of course with some axioms, one can imagine what kind of axiom can be. Like, for example, this axiom, like if we take alpha x plus 1 minus alpha x, it's give me x, okay? And another, of course, axiom. So this is what real convex sets. Of course, morphisms between convex sets, like convex map, it's maps of sets that preserve the structure, okay, that coming from this operation. And then we get a category of real convex sets, okay, this is a notation I use. But actually, we can define real convex set using the language of monad, okay? So there is an alternative way. Okay, let me show this alternative way. So first of all, what is, sorry, as algebra over the distribution monad. So let me tell you what is the distribution monad. So if we have a set X, so we have sets of all the distribution on X, okay? This mean like distribution on X, it's a map from X to R, like if for every element on X, a value on R. Now, what is R? R here is any commutative semi-ring. Okay, but one can think that we talk here about the non-negative rings. Okay, so if we have a map from X to R, such that just a finite number of them are not zero. Okay, so support it's finite, and the sum is 1. This is called the distribution. So all the distribution on X, this is the notation for this. Actually, this also can apply on maps. So this actually is a functor from sets to sets. More than this, this is actually a monad. Okay, this is a distribution monad. So it's also have the following structure map, the unit of this monad that sent every element X to this trivial distribution that give for this small x1 and the rest 0. And the multiplication of the monad, one can imagine how it's work. Like it's, if I have a distribution on the distribution of X, then we can do this average and get a distribution on X, an element here. Okay. So this is known things. So now we want to talk about algebra over this monad. So let me remind you what is algebra over a monad, or T algebra. Like if we have a monad T, what it means T algebra. So a monad T on any category C, it's not have to be sets or something. It's okay, any category C. If we have monad T algebra, it's an object in C with this morphism from Tx to X, with such that the following diagrams commute. So actually what it gives us, like part of the structure, like this, actually by this we can define, for example, monoids, some algebraic structure, or convexes, what we will do now. So in the monad, there is some of the structure, but this map actually, this gives a specific structure for X. Actually, this have to be pi X. This is not just pi, because it's specific for X. It gives the specific structure of X, okay, the relation inside it. Okay, so sorry, and of course, a morphism of T algebras, one can imagine that it's a map in C that preserves this map that gives structure. Okay, so this we have this equation. Okay, now we have the following proposition that the category of real convex sets, in the sense that we described before, like what I mean by this category, let me back before, we mean this, okay? This is the definition of real convex sets. This is the category of real convex sets. So the category of real convex sets is the same as the category of D algebra, where we take here the semi-ring to be the non-negative reals, okay? Okay, so this from this point of view, one can define the R convex set for any commutative semi-ring to be DR algebra with this distribution as is defined in the duality for convexity, the paper of Jacobs. Okay, so this the definition makes sense because of this proposition. Okay, well, now we can define convex sets for every when we deal with any commutative semi-ring. We have some properties on the semi-ring. It's not important for now. Okay, and we will use this notation for the D algebras, the DR algebras or the R convex sets for this category. Okay, we will use this point of view in order to define convex category. Okay, this is the fish of R convex set. We want to define R convex category. So in order to do this, we will show that DR actually acts, or it's a monad on categories. So let's do this. So if we have a category, of course, locally small category, like these homes are sets. So we can define the following category, DRC. This is the category. House look like this category. The object is the same object of C. But the home, it's by applying, like the home, it will be distribution on the morphisms of the original category C, okay? Home from X to Y is all the distribution on CXY. Okay, so how is the composition look like? So if we have a distribution on CXY, that means like it's a map in the home of XY in the category DRC, and we have distribution here. So by convolution, we will get a distribution on CXZ. What we mean, like the distribution on F, sorry, it's we take all the product of distribution on map here and distribution on map here, such that the composition give me F. All the ways to get F, we take all this distribution. This is what's called convolution. Okay. So this actually gives us a monad on categories. Okay, like for every category, we define another category, but this functorial, but more than this, there is a structure functor, like before, the unit. So one can imagine how the unit look like. It's identity on object, and it's behave on morphisms like the unit of when DR act on sets. The same for the multiplication of this monad. Okay, so when we have we show that DR act on is the monad on categories, so we can talk about DR algebra in categories. Okay, and we will call it a convex category. Okay, so this is the definition: the DR algebra in category. We'll call R convex category, and here is the notation we will use. Okay, I don't know if how I can. Yeah, okay, I will. I think you see this, right? Conv cat R. Okay, sorry. Okay, let's continue. This is what we call the R convex category, but let now okay understand what it's mean to be convex category. What that means. So actually, that means that for every home, like in this category, CXY is R convex set with this structure, because we define like R convex set is an algebra over the R or DR algebra, right? So we need this structure map. So for every CXY, we have this structure map, but this structure map for every home in C together is a functor. Okay, so it makes the following diagram commute for every 3 objects x, y, z. Like here, the composition is the composition in DRC, in the category DRC, which is the convolution we talked about before. Okay, so this diagram commutes. Actually, it's remind everyone sees the definition. It's remind us a category enriched by convex category, because a convex category have a monoidal structure. The Cartesian product is monoidal there structure, and one can talk about categories enriched by convex set. Okay, but it's actually something stronger than a convex category. So we have the following fact: like the category that enriched by R convex set is an R convex category, but the opposite is not true. Okay, like we can find the R convex category that it's not enriched by R convex sets. And the main example is the Kleisli category on sets. When the R act on sets, if we take the Kleisli category, then it's R convex category. This is a good example of R convex category, but it's not. I don't know, you see this or not? I don't know. It's down. You don't see, maybe, right? I have to do something. Oh, okay, I can read what it wrote here, but for some reason, okay, maybe I can do this. Now you can see, maybe it's better. Right, this. Okay, so here actually it's examples. The Kleisli category is example of R convex category that it's not enriched by R convex.
Would you like to put your slides full screen?
Yeah, I can, but for some reason it's not always work. Just a minute. This have to be. Yeah, it's not always work. I don't know why. Yeah, I just discovered it's just half hour before I try to. But it's now you can see, right? It's okay.
Yeah, we can see.
Yeah. Sorry about this. So let me back. Okay. So. Okay, just one word I want to say. Why it's not enriched by R convex sets, the Kleisli, because the Kleisli composition it's not convex. In order to be enriched by R convex sets, the composition have to be a convex map, but the Kleisli composition is not convex map. Okay, one can see it's easy. Okay. Okay, so now let's go to the second part of my talk, the phenomena of quantum contextuality. We want to show that convex category can be approached to this phenomena. So let me introduce to this phenomena. Actually, this is something coming from physics. So if we have 3 experiments, ABC with outcome 0 and 1, like for some plus minus the outcome for every experiment. We can do as much as we want this experiment, but for some reason we can't measure all of them together. Like the result, we can measure the result. We did this experiment 3 together, but as much as we want, but we can't measure all of them together and know the results. We can just every time measure 2 of them. In this case, actually, because we can do it as much as we want, we will get this table, okay, of probability. Like here, when we measure A and B together to get 0, 0, this probability, to get 0, 1, this probability, and so it's the same for BC, for AC. Of course, we know what we know about this tables. We know that the sum here is 1, the sum here is 1, the sum here is 1, but we know more. Like we know that the probability to get to A to get 0, we can sum both of this, right? But in the other hand, we can do this when he joined with C, like we can sum both of this. So that's why we get the following equations, okay? We'll get the following equation. But what actually surprised here is that this table is not coming from joint table. What I mean by joint table, it's something like this. This is a joint table, like when A, B, C is all of them 0, all of them sorry, 0, 0, 1, all the result we can get for 3 because we can measure all the result, but it's okay. We did all the result together. So one imagines that there is a table like this, and this is coming from the, like if we want to know here the AB 0, 0, we can take here, we can sum both of this because here AB 0, 0, 0, 0, okay? We can sum both of this and get this. So from this joint table, we can get all of this table, but not always. We have such a global probability table, okay? And this is something surprise. So people start to approach this phenomena in many, mathematically in many ways. But the way we want to talk about today, the way that actually my super advisor started, Jihan Okai, is a simplicial approach of this phenomena. Okay, it's understood. There is a questions here so far. Okay. Okay, so I can continue. So simplicial sets, let me remind you simplicial set because I want to define the simplicial approach to quantum contextuality. So a simplicial set is a collection of sets with the phase and degeneracy maps. Like what it means, it's like simplicial, like a graph. Like in a graph, we have just the vertex and edges, but here we have also triangles and things like this. Generalization of the graphs, one can think about this like this. Not exactly, but yeah. So in Xn, we have the n simplex, simplicial complex, but it's also generalization of simplicial complex. So in Xn, we have the n, like here we have the zero simplex, the vertices. Here we have the edges. Here we have the triangles, like this. And the faces give me the relation between things. The degeneracy have another rule. It's not important now. It's like we can see every vertex we can see as edge, right? In some way, every edge we can see as a triangle in 2 ways. But it's not important for now. So actually the faces is more important. So from X1 to X0, from all the 1 simplexes to the 0 simplex, we have 2 faces maps, like which tell me the faces of one edge. They have two faces. One edge have 2 faces. From X2 to X1, there is 3 faces because for triangles, the boundary of triangle has 3 edges, and so. Okay. So an important example that we will use is the nerve of Z2. Like we can, one of the nerve of category is a special case of nerve category. So what is the nerve of Z2 for someone who don't know this? It's in the 0 level, it's just a point. Like this is X0, like it's just a point. Here X1, the 1 simplexes is 2 elements. 0, 1, and here 4 element, and so on. And we have, of course, one can imagine how it's look like the degeneracy and the faces map. The face map is important. Like here's the faces map, one of them by omitting this side, one of them by omitting this side, one of them by some of them, and so on. Okay, why is this important? How we can use this in order back here to this probability table? How we can use this in order to in order to approach these things, in order to capture, sorry, this probability table. So the table of probability above, what I showed you before, can express as a simplicial map from X to the distribution on the nerve. What I mean by the distribution on the nerve, I mean to apply the distribution for everywhere here. Like we apply the distribution on this map and on the maps. Okay, we apply this functor. So if we apply this functor on this simplicial set, we get again simplicial set. So a simplicial map, we mean like a map level wise that makes a diagram from you. So if we have this map from X, when X is this simplicial map, what I mean by this simplicial map, I mean that we have 3 triangles, and they are the faces shown in the picture. Like this face for this triangle is the same as this face of this triangle, and the same here. Okay, so they glue together in this way. So if we have a map from X to dr of nerve of this Z2, this is exactly the three tables we have above, because actually from triangle, one can see that from triangle we will get here in the second level, like this is the 0 level, first level, 1 simplexes, 2 simplex, so we will get distribution on Z2 cross Z2. This is exactly what is the table. It was from Z2 cross Z2. And the compatibility, I mean, this is the compatibility like this equation. It's exactly what given in the simplicial identity, okay? Because this is simplicial map, okay? So, okay, one can check this. And then, actually, okay, sorry, I forgot to copy this picture. Okay, so this will remove when I move up. Okay, you will remember this. Okay, now and the global distribution, like this is the table what I wrote in the bottom, this one. Okay, one can convince that this is exactly the distribution of all the simplicial map from X to nerve of Z2. This I mean by the category of simplicial sets. So all the simplicial map from here to here we take is just defined by these three edges, and this is the distribution on this. And what I said that from a global distribution, this table, the long table, we can get all the three tables. It's exactly can define by this map, very easy map, from the global distribution to simplicial distributions, the tables. Okay. Okay. So, and then we define, okay, in general, of course, in general, we don't have to use the nerve of Z2. We can use any outcome space Y. Okay. And here is the definition. The definition is that distribution is non-contextual or classic, like it's come from classic physics, if it lies in the image of theta, like it's coming from joint distribution. Okay. So this is the definition. Okay, how it's related to convex category, how this things is related to convex category, let's see. So if we have if we have a T is a monad, we can look at this is all the algebra over this monad, T algebra, and we have this non-adjunction is the Eilenberg-Moore adjunction, of course. We have this adjunction. So we have this adjunction in this when dr act in categories, right? Like here is dr algebras over categories, a convex category. So we have this adjunction. And we have also, as we said, the monad dr acts on simplicial sets degree-wise, as we said before. So actually, we have this functor that sends simplicial sets to the Kleisli. Okay, this is the category of simplicial sets. This is the Kleisli. Like this is set morphism. On terms of object is the identity, but in terms of morphisms, this sends this morphism to the following morphism, the composition with delta. And if we take the transpose of this functor with this adjoint, we will get something related as to the map that define contextuality, this map theta. So let me show you the proposition. So the proposition says that the transpose of the functor of the following functor with respect to this adjunction is a functor. Okay, it's a functor in convex category. Okay, because we take this functor in categories. The transpose of this is functor here. This functor actually is the identity on object, but this functor actually is this theta that defines the contextuality on morphism. Okay, so this relation can tell us about that this actually preserves the convolution with the Kleisli composition, but it's not really one can apply this in order to capture contextuality. The other fact that one can applied, and it's good in order to capture contextuality, is when we talk about convex monoid. Convex monoid. So what is convex monoid? Is a convex category with a single object. Okay, this is a convex monoid. So in this case, when we have a convex monoid, which is actually one can see another way, like it's a convex set or convex set, which is a monoid, such that this the structure map is a homomorphism of monoid. And when we have a monoid, we can talk about the group of invertible elements in M. Okay, the group of invertible elements in M. And then we can come with something called the weakly invertible. What it means, the weakly invertible? It means like everything that coming from here by composition, that everything that is a convex combination of invertible element. Okay, when we have a convex monoid. An example of convex monoid is the following, actually, the set of simplicial distribution. It's example of convex monoid when Y is a simplicial group. What we mean by simplicial group? We mean like when all the faces and the Jersey map are homomorphisms. All the sets are groups, and all the faces and the Jersey map are homomorphism. In this case, this is R convex monoid. And then we can get, like in the case of the nerve of Z2, we have this. So we have the following theorem that, okay, we have some assumption on R on the semi-ring. Then it's the same, like to say that P is non-contextual is the same as to say that P is weakly invertible. Okay, the notation coincides here. Sure. Okay, so that is okay. I hurry a little bit because we started a little bit late. So thank you very much. Any questions?
Thank you very much for the talk. Is there one quick question? Maybe meanwhile the next speaker gets started.
Thank you for the talk. This story about distributions on sets that you then lift to distributions on simplicial sets, I'm just wondering, does this work for if you're replacing set with, say, measure spaces or some other structured category?
Yeah, actually, is this here actually worse, because actually if you think about simplicial sets is a functor from this delta opposite to sets. So actually just you here, just you compose this with the distribution. If you have another functor like this, if you're another, you can image this as a functor, you can always do this.